Hello, welcome everyone to this week's Bangalore Probability Seminar. Today we'll be having two talks, two a little different flavor talks. First is by Soumendu Sunder Mukherjee from ISI Kolkata. He joined in 2019, I imagine, and he'll be talking about learning under latent group sparsity via heat flow dynamics on networks. Soumendu.
Okay, thanks a lot for the invitation and the introduction. So, so this is a joint work with Subhroshekhar Ghosh at Anyways, who is in the audience. So let me start by describing the problem. So it's the usual supervised learning problem where you have data on n observation. You have n observations. Okay, yi denotes the response variable and xi denotes the explanatory variable. So I would give one example. So I'll come back to that example later in the talk. So think of yi being the let's say the temperature at Delhi at a certain month, and xi is a vector, and xi consists of the, let's say, the precipitations at different regions in Bay of Bengal or Arabian Sea. Okay, so we are trying to predict yi based on these observations xi, and you have n such observations. Okay. So x n cross p will denote the usual data matrix. Its rows are these observations xi transpose. Okay, and so the example I just gave, that's a regression problem. In general, I will be talking about generalized linear model. So y, the conditional expectation of y given xi is some function of xi transpose beta. And beta is an unknown parameter. So an example is a familiar regression model where yi is xi transpose beta plus some measurement error, let's say, or some noise. Another example would be logistic regression where yi is binary coded. So let's say yi is whether a certain email you received is spam or not. So the 1 means spam, 0 means not spam. And xi's are, let's say, the frequencies of certain keywords in the email that is supposed to detect whether it's a spam or not. So this is a popular model. This is the logistic regression model. So in this case, the conditional expectation is this logistic function of xi transpose beta. So we'll be dealing with the situation where the number of variables p can scale with n. So p can be large. By the way, feel free to stop me at any moment. Okay, so I'll be focusing on a certain type of regression problem where the parameters is the parameter vector beta is group sparse. Okay, so what do I mean by that? I mean that there are certain groups of variables which I denote by C1 to Ck, script C1 to script Ck, such that the support of beta is basically union of these sets C1 to Ck. Okay? So beta is supported on some of these groups of variables. Okay, and the thing is, we want to estimate beta from the data y comma x.
So this S is known?
S is not necessarily known.
Okay, thank you.
So examples would be, you could think of the locations at Arabian Sea as one group and locations at the Bay of Bengal as another group. Okay, and maybe the weather at Delhi NCR is only influenced by weather at Bay of Bengal. So in that case, the support of beta would be just the locations at the Bay of Bengal. All right.
One question.
Yes.
It just seems that support of beta, I mean, is there any specific reason to write it as unions of some sets? Because currently it just seems it's a subset of P. All
This
you're
is
saying
subset of P. Yes.
okay.
So this is a notation. This is a certain notation that will be useful later. That's why I'm writing.
Okay. Okay.
So we should imagine this as, so this within this CIS, the variables that you have, they are highly correlated in a sense.
Okay. Okay. Thanks.
All right. So how do you do it? So whenever you have sparsity, people usually tackle it by enforcing a L1 penalty. So this is the famous lasso penalty, where you basically, how do you do regression? You minimize the residual sum of squares. So here you throw in an additional penalty. You want the L1 norm of your parameter vector to be small. Okay. So this is your optimization problem, and this L can be the MSE, the residual sum of squares for regression, can be negative log likelihood or any other loss function that you want. And so this is the optimization problem usually solve. And so this is the usual reason why you do it. So without the L1 norm penalty, you have basically this. Let's focus on the regression problem. You have this loss function. The contours of this loss function are some ellipsoids, and the beta hat is the least square solution. And so here you want the solutions to be sparse. So this picture sort of explains why L1 penalty induces sparsity. So these squares are the balls or the level set of this L1 penalty. You can think about the sphere in the L1 norm. So these are the contours of constant residual error. So and you are penalizing via this L1 penalty. So as you increase this ball, it's more like to hit these contours at one of the corners, and that's why it will induce sparsity in the solution. This is unlike some other penalty, for example, the ridge penalty, where instead of the L1 norm, you take the L2 norm. Okay, that doesn't really induce sparsity. Okay. So this is the reason people work with L1 penalty in this case. But the trouble is that here this L1 penalty doesn't have any information about these groups. I have certain groups of variables which and beta is supported on unions of these groups. So if you do L1 penalty here, the problem would be that there may be certain variables which are in a certain group, but lasso will make one of them leave the model, the other one stays in the model, and you do not want that. Okay? You want all members of the groups to be either present in the model or absent from the model. So a way of circumventing this difficulty with lasso is that you take the following. You take a L1 penalty of the group wise L2 norms. Okay, it's very similar. Instead of the L1 norm, I'm looking at the L2 norm of each group and then adding them up with a suitable weight. Okay, so this is called the group lasso penalty. And again, you can look
So
at
why don't you do group wise L1? What is the difference?
Group wise L1 is basically similar to L1. It's a weighted L1.
Oh, okay. With your okay.
Right.
You're making it more outlier sensitive,
Yeah,
forcefully, so that it honors the group structure. Okay.
exactly.
Okay.
So either the whole thing would be 0 or yeah.
Right.
And this would be
question?
clear if I Manju has a question.
Soumendu, so just about this as well as the previous, does it? So this small l is a quadratic sort of term in beta, right? I mean this. So should you add a square or should you add? Does those things make no difference? The second one, whether you should add a square of L1 norm or is it L1 norm you add?
That does make a difference. That changes the shape of this ball completely. Okay. So you have to do the L1 norm.
No, L1 fine,
If
but
you
the two quantities you're adding, one is quadratic in
Yes.
beta, the other is linear, linear first order in beta, right?
Oh, I see, I see. You mean this one is quadratic? No, it so that is called square root lasso, where you drop this. They have qualitatively different properties. So,
Okay.
but we are more interested in the penalty. I mean, you can definitely use this without the quadratic term.
Okay.
So so that's another, that would be another loss function. The solutions would be different actually.
So I guess the GL beta penalty is comparable to, it's as if we are trying to do the lasso. So we have a linear L1 term, but we still want to respect the group structure. So instead of taking the direct L1 of beta, we do this more complicated thing.
Sort of, so this should be thought, so this is the restriction of beta to that group, and the whole thing either is, it tends to make the whole thing 0 or not. So yeah. It would be clear if I show you a picture of the corresponding metric ball. So this is the ball for group lasso. Here I have basically three variables. Variables 1 and 2 form a group, and variable 3 is a standalone group in itself. Okay, so it's basically like group lasso, basically like the lasso penalty, but you are basically adding a dimension to it. So it's like two cones merged together. Okay, and if you plot those contours, now those contours will tend to hit either this part of the this ball, which corresponds to this variable 3, or this circular section here, which corresponds to this group. It's basically beta 1 square plus beta 2 square equals to some constant. Okay, so in this way you enforce the group sparsity condition by introducing this penalty. Is that okay? All right. Now, if your loss function L is convex, then this is again a convex optimization problem, because you are basically adding some weighted norms. So you could use convex optimization techniques to solve it. One proper problem with this is that groups need to be known in advance, because you are designing the penalty. So the design itself needs the group CJ. Okay, so the groups need to be known in advance. So we are trying to, so in this work we are proposing a new penalty which doesn't require the group to be known in advance. So all right. So we'll assume that the group information comes from a graph on the variables. So remember, you have p variables. So there is a graph on the on these p variables, which gives you the group information in terms of highly connected subgraphs. Right. So L will denote the unnormalized graph Laplacian. And we'll recall this basic result from spectral graph theory, that your graph has k connected components C1 to Ck if and only if the Laplacian has exactly k0 eigenvalues. And the eigenspace of 0 in that case, one particular basis for that eigenspace is basically this set. So indicators of groups. Okay. Indicators of the connected components. So using this basic result, we will design a penalty which will encode the Laplacian inside the penalty, and we will not need to specify the groups in advance. Okay, so some notation. So the psi function is basically coordinate-wise squaring of a vector. Okay, and psi box inverse is sort of an inverse. It's not exactly the inverse. It basically takes first takes absolute value of each coordinate and then takes a square. Okay. So we'll introduce this new penalty, which we call hit.
Soumendu, sorry, can you just say again what is psi of beta? I missed.
Psi of beta is beta coordinate wise. So this is the Hadamard product. So beta I square.
Okay.
Psi of beta I is beta I square.
Okay. Thanks.
And yeah, so this is the penalty that we introduce. So you first take psi of beta, apply this heat flow operator e to the minus TL on that, and then take, negate the, apply this pseudo inverse, if you will, and then sum it up. So we'll see why we call it heat flow penalty. Okay.
So these square roots are all positive square roots, right? When you take
yes, all the square roots are positive square.
okay.
We call it obviously the heat flow penalty because there is the heat flow operator sitting in here. Okay, but why? Okay, so let's see a quick justification why it should induce group sparsity. So let's take the spectral decomposition. Let's say that you have exactly k connected components in your graph. And so this is the spectral decomposition of L. For the smallest k eigenvalues are 0. And this is the spectral gap. Okay. So let's compute e to the minus TL of psi beta. If you compute, we can take the first k component, and they would give you this, because the eigenvalues are all 0, and the rest of the terms are this. Now, if the eigengap, which is lambda k plus 1, is positive, it is positive in this situation. For t large enough, this should be approximated by this quantity. This second term should be negligible. If t is large enough, depending on the spectral gap. Okay. So for t large enough, therefore, if I apply my psi inverse and sum it up, it basically matches the group lasso penalty. So for t large enough, this penalty will converge to the, as t goes to infinity, it will converge to the group lasso penalty in this case. Okay. So a very intuitive way of thinking about it is that you have k connected components in your graph. So if you start a random walk on, let's say, one of the components and let t grow, at equilibrium, basically you'll hit the uniform distribution on that component, and e to the minus TL applied to this beta square will give you the expectation of beta j, where j is sampled from the uniform distribution, and that is exactly this quantity, right? So therefore, as t goes to infinity, this penalty will converge to the group lasso penalty. Okay. So so we want to so we basically replace all occurrences of group lasso with this new penalty. How do the level sets or the metric balls? It's not a metric anymore. The level sets look like. So yeah, so this is for t equal to 0.1. In the same example, we have two groups of variables. Variables 1 and 2 are in one group, and variable 3 is in a standalone group. So you can see that at t goes to, even for quite small t, approaches the corresponding group lasso metric ball. Okay. Okay, so the first problem with this is that this is not convex, unlike group lasso. Okay, so there might be local optima. So optimization is potentially more difficult. The nice thing about this is that subgradient descent or coordinate descent can be performed very easily. So I'll do a very quick subgradient calculation here. So remember, this lambda t beta is our newly proposed penalty. So if I denote by h this heat flow operator on the beta square, coordinates y square, that vector, then this penalty is nothing but sum of square root absolute hj. Okay, so if you take a derivative with respect to one of the coordinates, a very nice formula emerges. So you basically see this thing. If I denote this hj gradient of s hj times 2 by zeta, then the whole thing can be very succinctly written as this. Okay. So you're applying basically a heat flow on this zeta vector, and then taking Hadamard product with the beta vector. So subgradient computations can be done quite easily, and that is because you can estimate these quantities very easily using a Monte Carlo approach. So the ith coordinate of e to the minus TL at V would be exactly okay. So this is a typo, I believe. This should be V. This would be the expectation of V at ZT, where ZT is a continuous time random walk on G started at vertex I. Okay. So therefore, you can just simulate independent random walks started at I. Let's say we simulate B of them. The empirical average would be a good estimate of this vector, provided B is large enough. And the thing is, you just need to sample these B independent random walks started at each vertex at the outset. Okay, and then you can compute these vectors whenever you want.
Your F is probably a B in the last line.
Again, F is a V. That's a typo, right? Okay, thanks. So basically at the outset, you sample B independent random walks started at each vertex, and then you can compute all of these quantities. So that's our algorithm also. So what are some of the advantages? Where we are learning the group structure using only local graph information. So I only need to know the endpoints of these random walks. Okay, nothing more about the graph. If someone gives me the endpoints of the random walks, that's it. One crucial thing is we do not need to know the number of groups in advance. This is a very crucial point, because in group, I mean, an alternative to this would be, say someone gives you a graph which contains information about the groups. What you could do is you could do some spectral partitioning of that graph, and that would give you the estimates of these groups, and then you can just plug in the you can design a group lasso penalty with those estimated groups. But the spectral partitioning algorithms, they all require the knowledge of the true number of groups. In this case, we do not need that. I mean, of course, there is a caveat. We do need the eigen, we do need to run the algorithm till a large time t, depending on this eigen gap, which kind of depends on k. But in practice, what you can do is you can treat this parameter t as a tuning parameter and use, standard techniques for selecting tuning parameters, such as cross validation, to find the optimal t for your data. So a major advantage is that you do not need to know the number of groups. Okay, the endpoints of these random walks. So you remember, we need to sample B random walks per vertex. So we need PB many random walks. And we can just do it once and for all, and can be done in parallel. So this part is very fast. So we can show that to ensure a prediction error of at most epsilon, we need about log p max log 1 over epsilon many steps in each random walk. So not a lot of steps. And this is for typical graphs.
I have a question.
Yes.
So for all of this to make sense, are we actually assuming that we know the graph, or is it a generalized statement that given this set of nodes, we are taking in account all possible graphs?
About which statement? Here I am assuming that I know the graph.
No, the graphs. Okay, yeah. Okay, thanks.
So, but for the purpose of the, for implementing the algorithm, all you need is endpoints of random walks started at different vertices. Okay? You don't need the graph, the whole graph.
Furthermore, there is a way to construct the graph from data.
Yeah, we'll come to that later. Obviously in real data, you won't have a graph, so you can estimate some graph from the data itself. Okay. Yeah, so I'll just say that under some suitable conditions, you can show that its prediction error sort of matches the group lasso prediction error up to this approximation error. So this is the error that comes from, so this is coming from this is the error in estimating the group lasso penalty by our penalty. So as you see, if as you can see, if t goes to infinity, this goes to 0. And in fact, this term is essentially what's giving you these bounds on the number of steps that you need in each random walk. Okay.
Maybe you can mention something about the actual values of t that is necessary for like typical examples.
Yeah, we already saw one. So in most of our simulations, we saw that t equal to 0.5 suffices. So don't really need to run it for very long.
Sorry, this is for that thing with the 3 variables, or what is?
Yeah, this
that?
is for the thing with 3 variable. Yes.
Okay.
The eigengap in that case is 2.
In the beginning, you mentioned something about you also are interested in the case of very large number of variables. Is that correct? Or
Yeah. Yes.
okay.
Yeah. So in the real data applications with large number of variables, also t is pretty small.
Yeah. In our simulations, but so as long as your eigengap is large enough, t should be small, as you can see. So if there is good, as long as your eigengap is large enough, t can be small. And we'll see that in many real data applications, there is a nice cluster structure. So there are, let's say, 10 clusters, and then the eigengap is somewhat large. So small t suffices.
So this eigengap is really the smallest, smallest of the spectral gaps of the components, right? So
it's the smallest non-zero eigenvalue
Non-zero
of the
eigenvalue.
Laplacian. So,
right. But it is for each component is fast mixing. That's what it says. If the spectral, if that is large, each of the components is fast mixing. Okay.
Exactly.
I mean, if lambda g is not large, if it is small, then I mean, then the cluster structure is also pretty weak. I mean, in general, it will be hard to demarcate between what coordinates constitute a group and which ones do not.
Exactly. So it would be hard for group lasso as well if you want to apply spectral clustering on such a Laplacian where lambda is small.
Yeah.
So in some sense, lambda g being like the spectral gap being large corresponds to saying that there actually is some kind of a group structure underlying as the underlying truth.
I have another basic question.
Yeah.
So somehow I'm puzzled by the role of P. So suppose P is quite large, then somehow the spectral gap sort of doesn't play a role.
No, so P is the number of variables, but the number of variables, so those variables are partitioned into, let's say, Q many groups. Okay. And so this is coming from, so the spectral gas is the Q plus 1th eigenvalue of that. So each component can have large number of, for example, large number of variables.
So it's cluster-wise.
Yeah. So the variables are clustered. The number of clusters can be small, and this is related to the number of clusters. Okay. So yeah, and you can actually get faster arrays by assuming enough curvature in the directions of group sparse vectors. I will not elaborate more on this. You can look at the paper if you want. Okay, so let me show some simulations. So in this first simulation, I will generate data from Gaussian distribution with a block covariance structure, block diagonal covariance structure. Okay, so each block is a equicorrelation matrix. All entries, all of diagonal entries are constant row. Okay, so I'll generate data from this my explanatory variables from this distribution. So how do I estimate the graph? So I don't have a graph here. What I'll do is I'll take some estimate of this sigma. It could be the sample covariance matrix, but the sample covariance matrix is not a good estimate when P is large. So there are other estimates available in the literature. So you can take any off-the-shelf estimator of sigma and take the corresponding correlation matrix, and you will obtain the graph by the thresholding this sample covariance matrix, sample correlation matrix. Okay, so this is one way you can estimate a graph when any explicit graph is not given. Okay, so this is the result of applying these methods on these three methods on the data set I just on the simulated data set that I described. So all the explanatory variables are coming from this Gaussian distribution. Beta has the true beta, which is depicted here by this broken line, that has a group structures that aligns with the group structure of the covariance matrix. So beta is the support of beta is basically these two groups of variables. Okay, I think the other two. I think these two groups of variables, 1 and 3. So here n is 200, p is 100, so p is scaling with n, and these are the group sizes. And so I'm applying, so the green curve denotes group lasso, where I am extracting the group information by applying spectral clustering on the estimated graph, okay, with oracle knowledge of K. So I know that K, I did the simulation, I know that K is 4. So I feed K equal to 4 to spectral clustering. It gives me some estimated cluster structure. Then I design the group lasso penalty according to that and apply group lasso. So that is denoted here by this green line. The blue line and the red lines, these are basically the proposed penalty. One uses subgradient descent and the other one uses coordinate descent. You can see that both are giving you good results. One drawback that you can see of group lasso here is that it doesn't estimate the support very well. Here the signal is supposed to be 0, but the group lasso estimate still has some wiggliness there. So if you look at support recovery measures, so prediction error, estimation error, these quantities are similar across all three methods, but in support recovery, these penalties seems to work much better than group lasso. So when things are not 0, group lasso is, or when things are 0, group lasso is saying they are not 0. So that's why it takes a hit in specificity. Okay. Now, so this is a favorable situation. I'll show you a situation which is difficult. So here I will generate my data from Gaussian distribution on a graph, which has a latent block structure. So I'll take a graph from a stochastic block model with k groups. Okay, k equal to 4 groups, just as before. What is the covariance matrix? So the covariance matrix is the Laplacian. So basically this L plus epsilon I inverse. This is actually a massive Gaussian free field on this graph. Okay. So the situation is you have some graph which is coming from a stochastic block model with k equal to 4 groups. You have the corresponding Laplacian, and the x's, the explanatory variables, they are generated from a Gaussian distribution with this as the covariance matrix. So essentially, you're sampling from the Gaussian free field on this graph. In this case, again, sample covariance matrix is not a good estimate. You can estimate is using various techniques. So one technique is graphical lasso. So this does the following. You know that the inverse covariance matrix, which is L plus epsilon I, if this is sparse, I mean, this would be sparse if, okay, it may be sparse, may not be sparse. If it is sparse, then you can use graphical lasso, which essentially takes the log likelihood of this model and adds a L1 penalty on the entries of this sigma inverse matrix. So that's why it sort of enforces that the entries of the estimated sigma inverse matrix, they are sparse. Anyway, so there are many other methods of estimating L. So one could be this. So I do the same thing. I generate data from this model. My Y is coming from the linear model. Beta is again supported on the first on group 1 and group 3. Okay. Here you see that the performance is not very good for all the 3 methods. So here it's actually quite dense stochastic graph model. The within group connection probability is 0.5. The between group connection probability is 0.01. So it's very well separated, but still it's having quite, having a lot of trouble in finding the correct signal. If you look at the metrics again, the prediction error, estimation error, these are exactly, they're more or less the same. The heat flow penalties, they have better performance in support recovery as before. However, you can see that the part where the true signal is non-zero, it estimates the support correctly, but the estimation error is not so good from this picture. So we did a lot of simulations with various types of these models with various parameter settings, and we found that estimating the covariance matrix is quite difficult when you have a sample from a Gaussian free field like this. So here, let me show you a picture. So this is the true L matrix. Okay, and these are the estimated matrices. Estimated using, so we tried using a lot of techniques. Graphical lasso, sample covariance matrix, all of those essentially give you the same picture. So to estimate the true graph structure, you need a lot of observation compared to the number of variables. So about here you see that the cluster structure sort of emerges. Okay, so this is a good problem. I mean, we don't know how to improve on it. We have some ideas, but so we search the literature. There doesn't seem to be any existing method that has tackled this type of models. Anyway,
so the problem that the standard estimates of, say, sigma inverse don't honor the group structure well or something like that. What is the problem?
The standard estimate is the sample covariance matrix.
Yeah, that's not good when P is large. Right?
Yeah. The other estimates, they are good when N is large compared to P. So here P is 200.
Yeah.
And you see, like you need 4 times that for getting even something that is reasonable.
Okay.
And for the particular problem at hand, one possibility might be to actually use our heat flow based method to recover the support and then use a different method with the knowledge of that support. So,
yeah, but that doesn't work very well because the first estimated group structure is very crucial. I mean, if it's not that good, it converges to garbage. I've tried that. So.
Okay.
Okay, so let me end with a data application. So here I will try to predict the monthly temperature at the Delhi NCR region, which fortunately turns out to be almost like a 2.5 degree cross 2.5 degree box. So I already had data from, I found some, so there is a, I think National Weather Service at US, they collect data, weather data for all location across the globe. So I collected data for Arabian Sea and Bay of Bengal. So this is the correlation matrix of, so correlation between monthly precipitation in 2.5 cross 2.5 degree squares on Arabian Sea and Bay of Bengal. You can see that there is a very nice cluster structure here. So this part corresponds to this, and this thing, they correspond to Arabian Sea, and this part corresponds to the Bay of Bengal. So this is the correlation matrix after. So this is the weather data. So of course there will be trends and seasonal effects. So we removed all those things, and we're working with the residuals after removing the trends and seasonality. And then this is the correlation matrix between those residuals. Okay. So each point is here signifies, or each coordinate here signifies a particular 2.5 cross 2.5 degree box on Arabian Sea and the Bay of Bengal. So this is the estimated graph from here. Okay. So we applied group lasso as well as our heat flow based procedure with this graph. And so here's the result. So you see that, so this is a map that I don't have a source for this. I found it in Google Images. Conveniently, there's a 5 cross 5 degrees squares laid on it. My grids are 2.5 cross 2.5. So basically, these are my, this is one of the locations. And Delhi NCR is somewhere around here. So the weather at Delhi, the air temperature at Delhi NCR is my response variable, and the monthly precipitation at each of these coordinates. Okay, so these are my predictor variables, and so these are the estimated coefficients. We found that this portion of Arabian Sea and this portion of Bay of Bengal, sort of the precipitation there affects the monthly temperature at Delhi NCR. Perhaps not quite surprising, but yeah. So I think I'll end with that. Let me know if you have any questions. Thank you.
Perhaps we can unmute and thank Soumendu. Thank you, Soumendu, for a wonderful talk. So now I open the floor for some more questions.